This is a continuation of my last video on kind of like an introduction to sequences. In this video, we're going to talk about how you write the rule for a sequence, or at least utilize the rule, and the importance of looking a little bit further into a sequence before you kind of declare a rule. So it's as simply listing the first few terms is not enough to define a unique sequence. We must have what we call the nth term. Okay, so the nth term, basically, when we refer to the nth term, we say this is some a sub n. If our sequence is a, sub n, we can call it b sub n, or t sub n. I don't know. But we have some nth term or a rule for finding any term in the sequence. So that is, it's a way for you to say, well, if I wanted to find, well, what is the fourth term in the sequence? You could go plug in that 4 for n. Say go find a4. If you have the rule, you could go plug it in and find out what this is. So it says to see this, consider the following sequences in which both have the same first three terms, but the last one is different. So we say, you notice here we get a half, a fourth, an eighth, but this one gets a 16th and this one gets a 15th. And you'll notice here that I'm actually showing you the rules for both of these. So we say these are the rules for the nth term. Okay, so we say these are the nth term rules. And what these nth term rules do is they tell you how to find each term in the sequence. So for instance, right here, this is a4. We could go plug this in. We could say, well, this is 6 over 4 plus 1 times 4 squared, which is 16, minus 4 plus 6. And you'll notice here that we get, 6 over, it looks like 5 times, 16 minus 4 is 12, plus 6 is 18. So 5 times 18, and we'd say that the 18 and the 6 cross reduce, and this becomes a 3, so I get a 15th, which is exactly what we had gotten up here. But the nth rule is really important to the whole situation here. So sometimes we have the sequence, we have the outputs, the y values. You can look at it if you're looking at it like a function. And we want to work backwards towards, well, what was the rule for this? So what we're going to do is we're going to explore some best practices when finding a rule for a sequence. So it says write an expression for the apparent nth term of each sequence. You'll notice that when we write the nth term, it's related to the term in the sequence that it is. So like A4 was related to this 1/15th right here, but we needed to know this 4 and how it's related to the y value. So what we're going to do is this. We're going to modify this, and I'm going to suggest that we make a table. And what I'm going to do up here is I'm going to say that this is sub a sub, and I'm going to call it a sub n. And so these are like our output values, or y values, and we'll call this n. And what we're going to do is we're going to split this up into a table instead, and I'm going to write n as 1, 2, 3, 4, and so on and so forth. What we're essentially trying to do, guys, is this. We're trying to say, in general, what the heck am I doing to my n values to turn them into the y values, or the output, or a sub n values here? So, the question is like, well, what's happening to this every time? So first thing to do is notice any patterns. And I notice that this is going up by 2 every time. So when we say going up by 2 every time, I just want to point this out to you. If you're going to be working on sequences, this is what we call like a linear pattern, okay? And we refer to these later on as arithmetic sequences. But essentially, we say it goes up by 2 every time. This is very linear. So we say, well, what is it that I'm doing to my n values to get my y values? I say, well, am I doubling them? Well, I could take 2 times 1, and that would be 2 and not 1. And we say take 2 times 2, that'd be 4 and not 3. And 2 times 3 would be 6 and not 5. But you notice that every time I double these n values down here, if I were to just take 1 away from that, I would get what I need up here. So essentially we're going to say, well, then our rule, a sub n, our rule would be this. I'm taking my n values and doubling them, and then I'm subtracting 1 away from this to get this in general. So we say, in general, our nth term is this. And it would work. And we could test this out. We say, should I see if this works? We say, well, what if I did a5? I suspect I would get 9, and I get 2 times 5 minus 1, which is 10 minus 1, which is 9, which is exactly what we expected to get here. Okay, so let's take a look at, actually, we're going to go down to the letter C here. We say, let's cordon this off, and we'll isolate these numbers here. We say, all right, I want this. This is C sub n, some output for some input n. We say, here are the terms of a sequence, the first term to the 5th term. And what we want is this. We want the nth term. What is the rule for the nth term? And again, I notice that this one's going up by 4 every time. So if it's going up by 4 every time, I just want to comment on this. If it is a linear progression like this, then a lot of the time you're going to get like this y equals mx plus b looking rule. So we say c sub n. We say our slope here, I call it loosely slope, but we say it's going up by 4 every time. So we say really what I'm doing is I'm taking my n values and I'm quadrupling them. Okay, so we say 4n. So if I were to take 1 times 4, would I get 1? No, I would get 4, which is 3 more than 1. And if I were to take 2 times 4, I would get 8, which is 3 more than 5. And if I were to take 3 times 4, I would get 12, which is 3 more than 9. So what we need to do here is we need to just identify what it's changing by every time and then modify it here. So we say our rule is 4n minus 3. And of course, we could check this out. We say 4n minus 3 would give us, say, 6 here. We say 4 times 6 is 24 minus 3 is 21, and that's exactly what we would get next if we were to add 4 to 17. So now these last two rules on the right here, I just want to show you that sometimes they can be tricky. Sometimes you got to really kind of think about what's going on here. But essentially we say this is some rule b sub n, and this is some n, where n starts at our first term and goes on forever and ever, of course, and we want the nth term rule. What I want to point out here is that we have a sequence that goes from positive to negative to positive to negative to positive to negative. And whenever this happens, you want to build in a rule that essentially has this attached to it, negative 1 to the nth power. Now what this does is it switches signs. I mean, I'm not going to be able to write this in here very well. It switches signs is its kind of its job, and we're going to tack it onto whatever rule we see up here. So we say, well, what is it that I'm doing to these n values to get my b sub n values? So we say, well, I don't know, if I'm doubling them, 2 times 1 is 2, 2 times 2 is 4, and that's not negative 5, and 3 times 2 is 6, and that's not 10. So doubling doesn't work. Technically, I shouldn't point this out to you here, but think about what these numbers look like to you. They look like the perfect squares to me, except for they're all 1 bigger. That is, if I were to take 1 squared, I would get 1, and I get 2 actually. And I say take 2 squared, you would get 4. Well, they're saying you get 5. They ignore the negative. And 3 squared is 9. They're getting 10. So what we're really doing here is this: we're taking our n value and squaring it, but what we're also doing is just adding 1 to that. So what this does is it gives us 1 more than the square of the input, and this negative 1 to the n, that switches our sign. So what we need to do is we need to test this, okay? And I only say test this to see if it turns out the way we should. If I were to do b of 1, I get negative 1 to the 1, and I would get 1 squared plus 1. Sorry, that didn't fit very well. So we say b1 here, in this case, we would say be negative 1 times 1 squared plus 1 is 2. I would get negative 2, which I'm supposed to get a positive 2. So the interesting thing here is this, and I hope you're really paying attention. If you're ever off, just by a little bit, like all your positives should be negative and negatives should be positive. What you do is you take this n, here, and you make it n minus 1. And what that does is it offsets everything a little bit. That is, if you were to plug in 1 now, we'd say you get negative 1 to the 1 minus 1 power times 1 squared plus 1, which is negative 1 to the 0 times 1 squared plus 1 is 2. And we would get negative 1 to the 0, which is 1 times 2. We would get a positive 2. Whereas if you were to plug in a 2 now, you'd see you get an odd exponent, okay? So again, down here we say cordon these off. We'll make a table out of this. And oops. And and the thing is, these are kind of tough to see, but we say this is some rule d sub n and some n values here starting at 1 and going out forever and ever. But basically these are the perfect cubes up here. Again, I just wanted us to see a sequence that alternates its sign. So we say equals, and I should say negative 1 to the n for now. And really these are our cubes that I'm adding 1 to. That is, I'm taking all my n values and taking them times themselves 3 times and adding 1. So 2 cubed is 8. Plus 1 is 9. 3 cubed is 27, plus 1 is 28. 4 cubed is 64, plus 1 is 65. So we say, does this rule work? And again, we should test it. So we say d1 would be negative 1 to the 1 times 1 cubed plus 1. So we would get negative 1 times 2, which is negative 2, which is, I needed a positive 2. So again, what we're going to do is we're going to change our rule so it says n minus 1 on this exponent of the negative 1 base. Cheers.